Hi. Let's continue. So last time we considered the string equation on a half line with specific boundary condition. Let me repeat it. So we have this half axis, x more than 0, and so our problem is utt minus uxx is 0, u for t equals 0 equals f of x, ut for t equals 0 equals g of x, and u for x is 0 equals 0. So we consider this problem. This boundary condition is called Differential. Boundary condition, or simply D condition. One moment, I will take a new pen. It is called D condition. Today we consider another condition, namely the same problem, utt minus uxx is 0, u for t equals 0 equals f of x, ut for t equals 0 equals g of x, and this time we have the following: ux for t equal for x equals 0 equals 0. And this condition, boundary condition, called Neumann condition, or simply N condition. No, it is named after the mathematicians Differential and Neumann, who studied these problems, and many other which we also will touch in this course. So we have this problem. It is we are looking for a function u of xt, x in R plus, so x is positive, t also in R plus. And if you remember, in the case of D condition, we produced the odd reflection of the functions, and here we do the even reflection. So suppose uxt is a solution. We start from this. Suppose it is a solution. Now we consider the function v of xt such that it is equal u of xt when x positive, and u of minus xt when x is negative. So we take our function and we reflected it this way. So we find a even function such that for opposite values of x it takes the same values. Now, this means that in particular v of x0 is also an even reflection of f. It equals f of x if x is positive, f of minus x if x is negative. And Vt of x0 equals g of x if x is positive, g of minus x if x is negative. Yes? And now let us act in opposite direction. We consider the following problem. Let me denote this function. This function I denote by phi of x. And this is, instead of g, it will be gamma of x. Yes? And here, x in R, in the whole line. So we consider the initial value problem on the whole line. This time the initial function phi and gamma are even function. No? So you have the problem v tt minus v xx is 0 when x in R, t in R plus, v for t equals 0 equals phi of x, which is even, and vt for t equals 0 equals gamma of x, also even. And now we apply the same formula which we used already more than once. Let's find solution. V of xt equals 1/2 phi of x plus t plus phi of x minus t plus 1/2 integral from x minus t to x plus t gamma y dy. The same function. Simply I used this notation phi and gamma instead of f and g because f and g are defined on the half line and phi and gamma are defined on the whole line. And now we have this function. Now we can check that this function is also even. So v of minus xt, let us find it. 1/2 phi of minus x plus t plus phi of minus x minus t plus integral 1/2 integral from minus x minus t minus x plus t gamma of y dy. But the first is 1/2 phi of minus x plus t is equal to phi of x minus t because phi is even plus phi minus x minus t is equal to x phi of x plus t because phi is even plus integral here 1/2. The function gamma is even, and so if you take the opposite values of the limits and change place of them, the result will be the same. So it is x minus t, x plus t, gamma y dy, which is v of xt. So this even function which is in place of initial conditions result in even solution. Now let us return to the functions on the half line. If it is x, this is t, let us draw a diagonal here. So if you are in this domain number 1, here x more than t, more equal than t if you take on the diagonal, then you see that here both x minus, it is a point xt, x minus t and x plus t are in the positive domain of positive x. And here the function phi equals to f and gamma equals to g. And so here we can write in domain 1, u of xt equals v of xt equals 1/2 f of x minus t plus f of x plus t plus 1/2 integral from x minus t to x plus t g of y dy. We replace here phi by f because on the positive line, half line, they are equal. Now we have the domain 2. Here is x less than t. So in domain number 2, we have the following. Let me draw the picture again. If you are here, yes, xt, x minus t, x plus t. No, x, we are interested in positive x or non-negative, yeah? So x plus t is definitely positive, but x minus t is negative. But instead of x minus t, we can consider symmetric t minus x. Yes? And have the following. U of xt equals 1/2 f. Instead of f of x minus t, it is here 1/2. I write phi of x minus t plus phi of x plus t plus 1/2 integral from x minus t to x plus t gamma of y dy. Now phi of x minus t is equal to f of t minus x. So I write 1/2 f of t minus x, and phi of x plus t is f of x plus t plus f of t plus x. Now, the second term, this integral, let me write it as a sum. 1/2 here, integral from x minus t to 0 plus integral from 0 to x plus t gamma of y dy. Yeah? And what it is, let me move here. This again equal to 1/2 f of t minus x plus f of t plus x plus 1/2 integral. Here we have integral from x minus t to 0. But the function, it's also gamma. The function gamma is even, so we can replace integral from x minus t to 0 on integral from 0 to t plus x. 0 t plus x gamma y dy plus the second integral from 0 to x plus x plus t. 0 to x plus t gamma y dy. And again 1/2 equals 1/2 f of t minus x plus f of t plus x plus from this integral is again a sum of integral from 0 to t plus x plus integral from t plus x t minus x to integral x plus t. So we have 2 times this integral and once this. So result will be integral from 0 to t minus x gamma y dy plus 1/2 integral from t minus x to t plus x gamma of y dy. Yeah. So we have this interesting formula. Okay, we are done. From this formula, it is not immediately seen. No, it is seen because it's the same formula which was before. So we have a function which is even. From the beginning, this is a solution in the whole line, on the whole line, x line, which is for all t is even function of x, yes, and if this function is regular, say differentiable, at every point. Then its derivative at 0 is 0. So right here, if say v of x defined on the whole line is even, v of minus x equals identically v of x, then v prime of 0 equals 0. It is clear? No, why? No, simply if we consider the function v of minus x, yes, equals w of x. On one hand, w prime of x is the same as v prime of x, yes, because it is an even function, so nothing changes. W of minus x equals w of x. Yes, on the one hand. On the other hand, if you consider w prime of 0, then after this, just a minute. No, I don't need. V prime of minus x equals minus v prime of x by the rule of differentiation on one hand. So v prime of minus 0 equals minus v prime of 0, which means that v prime of 0 equals 0, the only number such that minus this number is the same. Okay, so why I am saying so? That it is a big if. If the function is regular, differentiable, then it satisfies this condition. The only thing that why it should be regular. Yes, why it is regular. We will discuss it next, and now I wanted to consider some examples. We have a formula, so let us see what it gives us in some particular cases. So, example, f of x equals x, g of x equals 0. Yeah? So let us apply this formula. U of xt equals, no, this term is, this first term is interesting, the second is 0, because g is 0. No, it's not gamma, it is g. Yeah, it is 1/2 so we have to distinguish between two domains. First, x more than t. U xt equals 1/2 f of x plus t, it is x plus t plus x minus t. Yeah? F of x plus t plus equals x, t cancels, it equals x. So in the domain number 1 it is x. In the second domain, x less than t, less or equal. U of xt equals 1/2 f of t minus x. T minus x plus t plus x equals t. Yeah? So how does it look? Let me draw the value, the graph of solution for different values of t. For t equals 0, it is equal to f of 2x. T equals 0. For t equal 1, so when x more than 1, it is the same, yes? For x less than 1, it is t, it is 1. So let me erase this. So this is the graph of solution for t equal 1. Now for t equal 2, we have a similar thing. Here for x more than 2, we have the same function, and here it is equal to 2. Yeah? So you can see the pattern. Now if you consider this initial condition, initial function value, this is t equals 0. This initial function. You can see that this function does not satisfy the Neumann condition. Its value at 0 is its derivative, x derivative at 0 is 1, it's not 0. But then instantly it becomes 0. So we can pretty much admit that at some moments, maybe some discrete moments, the Neumann condition can break down. So solution for all moments except the first moment, the solution satisfies the Neumann condition here. Now, okay, let us consider now other example. It is equally simple. This example is f of x is 0, g of x equals x. Yeah? In this case, the first term is 0 and remains the second, the third term. In the domain, so it is if x less than t. And if x more than t, we have the previous formula. So x more than t, more equal than t. Then let us substitute it here. no, we have to use the formula for the whole line. U of xt equals integral 1/2 from x minus t to x plus t, x dx equals, now let's find it, 1/4 x plus t square minus x minus t square equals 1/4, because 1/2 from here and 1/2 integrating x. It is, let me write better, y dy. It is 1/4 x square plus 2 tx plus t square minus x square plus 2 tx minus t square equals, so all terms cancel, it is equal t times x. So it is here. Now in the second domain, x less than t, we have should use this formula. U xt equals integral from 0 to t minus x y dy plus 1/2 integral from t minus x to t plus x y dy equals 1/2 t minus x square plus 1/4 t plus x square minus 1/4 t minus x square. Yes, I integrate it, equals 1/4 t minus x square minus plus t plus x square equals 1/4 t square minus 2tx plus x square plus t square plus 2tx plus x square. It is 1/2 x square plus 1/2 t square. Yes, so we have this. No, it is not even obvious that it should be continuous function, but let's check it. So of course it's continuous, but we have to check it when x equal t. So in domain 1, u of tt equals tx t square. In domain 2, I mean, if you approach the diagonal from below and from above, u of tt equals 1/2 x, 1/2 t square plus 1/2 equals 1/2 t square plus 1/2 t square equals t square. So it's okay. Now, how does it look, the graph of the function? So at the moment t for x for x more than t, the function is t times x. So here it is linear function, so it is x. Yes, it is u of xt. For t less than x, it should be equal to 1/2 x square plus 1/2 t square. So it is t square, it is 1/2 t square. It is like this. So it is a piece of parabola, but here they have equal derivatives, so it conjugates smoothly. So this is the function solution, graph of solution u of xt. Now we can see that when t grows, it will behave like this. Yes, I'm sorry. X. When t is 0, it is t times x, t is 0, so this is t equal 0. For t equal 1, here is 1/2. It is t equal 1. For t equal 2, here 1, 2, 3, 4. Here, let me draw it. And here is 1/2 t squared, it is 2, yeah, so this is solution, and so if you continue, this function is also hit 0. So this is the graph of solution. So it consists of a piece of straight line and piece of parabola, and so on. No, we can, how to say, visualize it if with Differential condition the physical image is that we have a string and it is fixed at the end point. Yes, it is Differential condition. For the Neumann condition, it looks like this. We have a vertical bar, this is the string, and we can attach a small ring around this bar, so that it can freely move up and down, and so it's naturally will look like this. If it is weightless, so it has no inertia, then it more or less automatically ensures the Neumann condition. So du dx is 0. That's it. Now, it is little to add here more, and I wanted to go to the next case, even a little bit more tricky. It is called string equation on a finite segment. So suppose we solve equation utt minus uxx equal 0, but here domain is say x between 0 and some L. So it is a finite segment. T positive. So we, as usual, should define initial conditions. U for t equals 0 equals f of x. Ut for t equals 0 equals g of x. Yes? And what to do at the endpoints? We also have to say something about the function at the endpoints. We have already two sorts of boundary conditions, D condition and N conditions. Yes? And we can have here four combinations. So here D and here D, or here D, here N, here N, here D, and N on both ends. So we have four combinations, and I did not tell you that, of course, we can consider many more sorts of boundary conditions. These are the most classic conditions. Now, let us start from Dirichlet condition on the right and on the left hand. So we write at condition U for x is 0 is 0, and U for x equal L is also 0. So we have one equation and four conditions. These are two initial conditions and two boundary conditions. So our problem is swelling in front of us. Now, what to do? What can be our tactics? Our approach can be the same. The use of odd reflection in the end, at the end points. So this is 0, this is L. Yeah? Let us look for solution in the whole, on the whole line x-axis, yes, and for all positive t, such that this solution, if you flip it here at 0, then it changes sign. So this means u of minus xt equals minus u of xt. Yeah? But this is not enough. We have to also solution that it is odd with respect to the point L. So what does it mean? How can you express analytically that solution, that if you reflect it here, put a mirror here and reflect it, yes? Under this reflection, 0 goes to the point 2L, and the point 2L goes to 0. So the point x, any point x, is changing to the point 2L minus x, yes? And this point 2L minus x again goes to x, yeah? So u of 2L minus xt equals minus u of xt. What else? In fact, it is enough, because if you can reflect it in the relative to the point 0 and relative to the point L, then if you reflect it relative to the point 2L, yes, how we have point x, and here is 4L minus x, u 4L minus x t equals minus u of xt. But in fact, this transformation u for L minus xt can be reached if you produce the following. No, okay. I think you can. It is a problem. Problem not in assignment. So it is a problem which is not related to our to the main content of the course. So if prove that if u of xt, no, t is parameter, satisfies say 1 and 2, then it satisfies three, and generally u of 2nl minus x t equals minus u xt. Yes. So in fact, these two symmetries, I would say antisymmetries of the function, is enough to prove that it is antisymmetric relative to all these point L to L minus L and so on. So you can think about it, but I don't tell you from the beginnings that it is not much related to the main content of our course. No, okay. So in this case, we have to continue the function f by the same formula. Continue f of x, g of x by the same formula. Phi of x equals fx if x between 0 and L. Now it is phi of minus x equals minus phi of x, phi to L minus x equals minus phi of x, phi 2nL minus x equals minus phi of x for n equal 0 plus minus 1 plus minus 2 and so on. So the function phi and the same the function gamma of gamma of x equals g of x if x between 0 and L. So we first define function on this interval from 0 to L, and then using this equality 1, we continue it in the odd way on the interval from minus L to 0. Yes, just flip it here. Now, after this, we take this interval from minus L to L and flip it from L. So here is from L to 3L. Yes. Then we take, so we have a function defined already here. Then we move it further, continue it further using the same reflections. But every time the interval on which the function phi and gamma are defined becomes longer and longer. So eventually we'll define it on the whole line. That's it. So how can we imagine solution of this equation? Very simple. We take this continued function after all these reflections, and we apply our formulas for solution of initial value problem on the whole line. These formulas which we already know. So let us consider one example. F of x equals 0. G of x equals 1. For this first is defined between 0 and L. x 0, it is L. Here the function is g is 1. F is 0, so I don't draw it. G is 1 here. So from between minus L and 0, the function should be odd, should be minus 1. Yes? Then we reflect it here, so it is 2L, and change sign. This means that here it is minus 1, and here it is 1. Oh my God. Now we flip it here. It is minus 2L minus 3L and so on. So we have the function. How can you express this function gamma of x equals, so it is 1 when x between 0 and L, minus 1 between L and 2L, and so on. So we have to take minus 1 to the power integer part of x divided by L. It will not help us much, but why not? Okay, so this is our function gamma of x. And now we define solution of the following initial value problem. V tt minus v xx equals 0. V for t equals 0 is phi of x. Vt for t equals 0 equals gamma of x. This is our initial value problem. Now in our case phi of x equals 0, so we can not write the first term, and we simply write v of xt equals integral from x minus t to x plus t, gamma of y dy, 1/2 dy. Yes? No, now we have to find what is gamma of y. Equals, let me write, 1/2 gamma capital of x plus t minus gamma capital of x minus t. Gamma capital of x, capital gamma of x equals integral gamma small x dx. It is a primitive function. Now, what is the primitive function of this function? No, for simplicity, let us set L equals 1. then we can easily write, if you integrate from 0 to x this function, so what will happen? Here the function integral of 1, it is x from 0 to 1. Now it is minus 1 at the point 2, it is again 0. Then at the end it is 2. At the point 3, it is again 1. At the point 4, it is 0, and so on. Such the it is minus 1, minus 2, and so on. So we see this function. No, okay, this function is gamma of x. Yes? And now we have to find this function. Fortunately, we see that this function is periodic with period 2. Yes? So we don't need to look for this function for all t. It is enough to find this function uxt for t from 0 to 2, because after that it repeats periodically. Yes, so this function. Now let us draw it. Gamma x minus t minus gamma of x plus t. So this is 0, this is 1. Okay, no, this is 2. So the function gamma is, no, I draw not to scale, like this, gamma of x. Yeah. Now gamma of x plus t minus gamma of x minus t. So for t equal 0, this is 0. Yes. Now for t between 0 and 1/2. Why 1/2? Just a minute. Sure. One moment. Let me write it here. U of x, v, t equals 1/2 gamma of x plus t minus gamma capital minus gamma of x minus t. So let's draw the graph of this function for t equals 1/2. Gamma of x plus t, it is 0, 1. The tent is here, 1/2. It is minus 1/2. Let me draw 3/2. Yes, it is the same function, but shifted to the left by 1/2. Now minus gamma of x minus 1/2. So it is minus 1/2. So now just a moment. It is the summit moves yes, it starts at 1/2 and goes 1/2 and 3/2 to 5/2. Yeah. So the second function is this. Now it is gamma of x plus 1/2. It is gamma of x minus 1/2. We have to take the difference between them. Here it is this. Here it is this. Yes? And here it is a linear function, so between these 2 points. Yeah? So this is, you have to take 1/2. This is 1, so this means that this is 1/2. This is minus 1/2. So we found our one moment. Let me do it again. It is 1, it is 2, minus 1, minus 2. So what is gamma of x plus 1/2? I have to take this function and move it to the left by 1/2. So the summit will be here. This. This function. It is gamma of x plus 1/2. Gamma of x minus 1/2 is this 1 1/2 yes, this is gamma of x minus 1/2. Now this is the point 1/2, this is the point 1. Okay, so yes, then it should go this way. Yes. So gamma of x plus 1/2 is this. This gamma of x minus 1/2, this is. It is here. Now we have to take the difference between these two functions. So at 0 it is 0. At 1/2, one moment. At 1/2 it is 1/2. At 1 it is 0. And we don't need to find the sum or difference outside of this segment. We are interested to solve between 0 and 1. So here we constructed this solution. So this is solution for t equals 1/2. So what is solution for t equal 1? For t equal 1, gamma of x plus 1 is the following. It is gamma of x plus 1 minus 1. Gamma of x minus 1 is the same because here we moved it by half, by 1 to the left, and if we move it by 1 to the right, then this tent will stay here. So it is gamma of x minus 1 equals gamma of x plus 1. So the difference is 0. So solution is 0. So it would be interesting to find for intermediate values of t, say t equals 1/4. Let us do it. This way. So it is 1 gamma of x, gamma x plus 1/4, so 1/4 is this, 3/4 also, one moment, minus 1/4. So it is gamma of x plus 1/4. Gamma of x minus 1/4. It is here. Yes, like this. So let us find the difference. Here the difference is 0. At this point, at the point 3/4, this so it is gamma x plus 1/4, and it is gamma of x minus 1/4. Yes. So here it is 1. It is 1 minus 1/4. So here it is equal to 1/4. And here it is 0. one moment. If you take difference between this and this, here it grows to this value. No. Here it goes this way. Yes. So this means that here it is 0. Here it is this. Then it stays constant. It stays constant till here. And then it goes down to 0. Yes. This. So it is 1/4, and this is also, it is 1/2. Yes. So let me draw it again, what we get. It is the following. It is 1. It is 1/4. It is 3/4. Here we have 1/2. Just a minute. No, it's 1/4. Yes. So this is our solution at the t equal 1/4. For t equal 1/4, this is the graph of solution. So now we can even create sort of a movie. So for t equal 1/4 we have this. For t is t. One moment. Zero, 1. It is a graph of solution for t equals 0. This is graph of solution one-fourth, 3/4, t equal 1/4. It is 1/4. This is graph of solution t equal 1/2. Now then we go again back. We have the same picture. T equal 3/4, and for t equal 1 we have again 0. Let me draw the direction of velocity. This is growing, this is staying in place, this is going down, this is going down, and then it will repeat for t, it is for t equal 1. For t equal 1 and 1/4, we'll have this picture. It is t equal 5/4. Then we have this picture. Yeah, it is going down. It is for t equals 3 seconds. Then we have this picture again, but this time it goes up. T equal 8/4. And then you have initial picture for t equal 2. u is 0 and du dt is 1. So you see this process of vibration is going up, then reaches its summit, then goes down, then it reaches this negative maximum, and then again goes to 0, and then it all repeats anew. So we have a periodic solution, time periodic solution, which looks very close to, resembles closely vibration of a guitar string. Yes? In fact, it is guitar string, motion of guitar string. Just imagine, let us start from this situation. We fixed the end points of the string, and then we took the midpoint of the string, pulled it a little bit up, and then released. So what will happen? We will see this picture. Yes, then the string will return to initial, to the straight line, but it has velocity directed down. Then it will go down, you see, opposite direction. From here it goes down, then it is opposite to what was in the beginning, and then it reflected here and started moving up. Yes, it moved up and then returned to this same configuration. So this happens when we play guitar. Now, what can be said else? If you need, you can impose, say, the Differential condition in one end and Neumann on the other end. In this case, we have, when you reflect it in the Differential end, we change sign. When reflected in the Neumann end, we don't change sign. Yes, so, and after this infinitely many number of these flips, we continue our function to the whole line. The functions f and g, and then apply these same functions. So all the following will depend on what you need. We can also consider on the two sides the Neumann condition and so on. It is beginning of very rich theory of such equations, because we can modify conditions, we can say consider the Neumann condition. Instead of Neumann condition, we consider the freely moving end point, freely moving on the vertical bar, but with some mass attached. Yes, it is also a fine problem, say coupled equation of string and mass motion. It is no, we have, I would say, even at this point, we have infinitely many interesting problems. But I prefer to stop here. Maybe I'll give a couple of problems as in the assignment about this, because we have very important theoretical issues here, and these theoretical problems which we consider are maybe for this theoretical course are even more important than these particular problems. We have no time to consider these problems in more detail, and so starting next week we will more concentrate it on the theory, because for now it looks like we live in 18th century and we don't know exactly what is continuous function, what is differentiable functions, and so on. So we have to proceed closer to what analysis. Yes, and make more rigorous consideration of all these things. No, fortunately, we have a formula for solution, so it makes life much easier. Okay, let us finish this time. Have a good time. Bye.